Welcome back to Math 104. Here is another expected value example, another problem type involving expected value. The operators of a blood drive are eagerly hoping that a type O negative donor will appear. Type O negative blood can be given to recipients of any blood type, so if you're running a blood drive, it is especially good news if type O negative donors show up. In the United States, 7% of the population has type O negative blood. We interpret this to mean that at a blood drive, each donor, individually, has a 0.07 probability of having type O negative blood, and we will assume that that's independent of all the other donors who show up. In other words, we're going to think of each donor as a Bernoulli trial with probability p equal to 0.07. We'll regard it as a success that a donor does have type O negative blood. Now suppose that the blood drive will continue until a type O negative donor is found, at which point they'll stop. They just need one donor with type O negative blood. But if a type O negative donor has not appeared by the 5th person to be tested, the blood center will give up and cancel the blood drive for the rest of the day. Wow, they are really impatient. It's helpful to start drawing the tree that goes along with this experiment. At the first testing, either the first person tested has O negative blood, or the first person tested does not have O negative blood. And it is with 0.07 probability that the first person does have O negative blood, and therefore the blood drive can stop right there. And it is with a 0.93 probability that the first donor does not have type O negative blood, and therefore the blood drive needs to continue. So there will be no further branchings from this point, but from here there will. Given that the first donor does not have type O negative blood, the second donor could either have type O negative blood with probability 0.07, or not have type O negative blood, have a blood type different from O negative. That has a probability at stage 2 of 0.93. And so it goes through several more branchings. We might need to test a third donor, or a fourth donor, or possibly a 5th donor, but there will be no more branchings after that. Notice how this tree is quite different from the full tree that we've looked at before for experiments that involve Bernoulli trials. Our first question is, what is the probability that the blood drive will be cancelled without finding a type O negative donor? In order for that to happen, it would have to be that 5 donors come in, and one after the other, they all have a type different from O negative. We can think of this as just following a certain path through the tree. So 0.93 at stage 1, times 0.93 at stage 2, times 0.93 at stage 3, times 0.93 at stage 4, times 0.93 at stage 5. In other words, 0.93 to the 5th. Or, if you really wanted to, you could write this as 5 choose 0, so the probability that there are 0 successes in 5 trials. So the probability of a success raised to the 0 times the probability of a failure raised to the 5th. These are the same thing. This equals approximately 0.6957, so very nearly 70%. There is a nearly 70% chance that they're just not going to find the type O negative donor they're looking for. So we're still doing some pure probability questions before we get to the expected value question. Our next probability question is, what is the probability that the third donor to appear will have type O negative blood? Now notice, we've set this up in such a way that the blood drive continues only until the first type O negative donor is found. Once they've found a type O negative donor, they can go home. That means that when we talk about this event, that the third donor to appear will have type O negative blood, that means that in this event, the first 2 donors do not have type O negative blood. If they did, we would never have gotten to the third donor. So here we've got a non-type O negative donor for the first donor, then a non-O negative donor for the second donor, and then, yes indeed, an O negative donor for the third donor. This is the probability associated with a particular path through the tree. Not O negative, followed by not O negative, followed by O negative. So 0.93 times 0.93 times 0.07. That is a certain event. Its probability is approximately equal to 0.0605. There is only slightly greater than a 6% chance that this search for a type O negative donor will end specifically on donor number 3. Not earlier and not later, but specifically on donor number 3. Now that we've computed a couple of probabilities, we're ready to handle the expected value computation. We can ask, what is the expected number of donors to be tested at this blood drive? As usual, that's in the mathematical sense of expected. That means we need to think, what are the different number of possible donors, and what is the probability of each one? Well, there could be one donor, and then we're finished. There could be 2 donors, and then the blood drive ends. There could be 3 donors, or 4 donors, or 5 donors. But there could not possibly be more than 5 donors tested at this blood drive, because it has been set up so that it ends after the 5th donor, if it even gets that far. There could be 1 donor, there could be 2 donors, that's another possibility. There could be 3 donors, that's the one we just found the probability for. There could be 4 donors, that 2 is possible. There could be 4 donors, and then exactly at that moment the blood drive ends. Or there could be 5 donors. If it gets to 5 donors, maybe that 5th donor has O negative blood, and maybe that 5th donor doesn't have O negative blood. Either way, there won't be a 6th donor. If it even gets to the 5th donor, that donor will certainly be the last. Now, each of these possible numbers of donors has to be multiplied by its probability. 1 donor times the probability that the blood drive ends after 1 donor, and that probability is 0.07. The only way the blood drive can end after 1 donor is if that donor already has type O negative blood. How about 2 donors? Well, by similar thinking to what we were just doing, that can only happen with a non-O negative person followed by an O negative donor, with probability 0.93 times 0.07. 3 donors, we just figured that out. That's 3 donors times 0.93 squared times 0.07. Right? All of these are going to be added up. Okay. Then we've got 4 donors times 0.93 to the 3rd. There would have to be 3 non-O negative donors followed by a single O negative donor. And finally, this is the tricky one, 5 donors times the probability that the blood drive lasts exactly for 5 donors. This is going to be 0.93 to the 4, and that's it. Just 0.93 to the 4th. Why are we not multiplying this 0.93 to the 4th by some other thing, by 0.07 for example? This right here is the probability that the first 4 people don't have O negative blood. And that is exactly what it takes to make the blood drive last until the 5th donor. Once it lasts until the 5th donor, it doesn't matter whether that 5th donor has O negative blood or not. That 5th donor will be the last donor. So if you really want, you can think of this as 0.93 to the 4th times 1. In other words, person number 5 can have whatever blood type, and it still contributes towards this event. We get approximately 4.35 donors. On average, this blood drive will last through 4.35 donors. Notice how close this number is to 5. What we've really done here is to take the numbers 1, 2, 3, 4, and 5, and weight each one by its probability. So we've taken a weighted average here of the numbers 1, 2, 3, 4, and 5. That weighted average ends up being rather close to 5. It ends up being between 4 and 5 because the probability that it will require 5 donors is so large. We computed it before. There's almost a 70% chance that we'll need 5 donors. That really pulls the weighted average very close to 5. Another way to phrase the question we just asked is, what is the expected number of Bernoulli trials needed to produce the first success, with a limit of at most 5 trials? Before we were asking, what's the number of successes in a certain number of Bernoulli trials? Now we're turning it around. We're not asking for the expected number of successes, we're asking for the expected number of trials. That is a different question, and it is not a job for the n times p shortcut. Before going on to the next video, answer the following questions. Suppose that the operators of this blood drive are a little bit more patient and decide that they will wait at most until the 6th donor instead of the 5th, after which they will either have found a type O negative donor or they will cancel the blood drive. So it's exactly the same setup, except that it lasts potentially until the 6th donor instead of the 5th. What is the expected number of donors to be tested at this blood drive, in the mathematical sense of expected? A different blood drive on the other side of town has a different approach. They gather 6 donors and test all 6. What is the expected number of people with type O negative blood in a group of 6 donors? Again, in the mathematical sense of expected. Think about how these two questions differ from one another.